moved the modern battlefield looking for targets. They have become so effective that anything that can be detected can be destroyed. But modern electronics can also be used to defend aircraft and ships by blinding the sensors. This seesaw battle of electronic wits is the Wizard War. One of the most revolutionary inventions in 20th century weaponry was radar. Radar for the first time permitted the detection of aircraft and ships at great ranges, 100 miles or more.
Radar became important immediately before World War II when the performance of aircraft, the speed and the altitude performance of the bomber aircraft reached a point where the fighters could no longer take off and reach them before they got to their target. Before that, they used sound location systems and also ground observers, and these guys just couldn't give enough warning. You needed about 50 miles warning to get the fighters off, and that was why radar became very important. Later, when it came in, radar made possible night air interception, and you just couldn't do it without radar. So for all of those reasons, every warring nation in World War II invested a lot of effort into developing radar.
Radar works by emitting a beam of electromagnetic energy. When the wave of energy strikes an object, such as an aircraft, some of the energy is reflected back to the radar antenna. This reflected signal is used to determine the location of the target aircraft, as we see on the radar screen here. Radar's earliest victory was in the Battle of Britain in 1940. By detecting the German aircraft early, British defences could be coordinated to best repulse the German attack. Spitfire fighters could be scrambled to intercept the incoming bombers. Allied advantages in radar technology played a crucial role in later battles, including the critical Battle of Midway in the Pacific. As one American scientist noted, radar may not have won the war, but without radar, it might have been lost. But the Axis powers were not totally blind to the advantages of radar. Germany developed a sophisticated radar air defense network in the hopes of stopping British and American bomber attacks. German cities and industrial sites were subjected to a merciless pounding day and night by Allied bombers. The Germans struggled desperately to blunt these attacks. In the first line of defense, long-range surveillance radars were used to detect the bombers and to vector fighters against them. Second line of defense, fire control radars could help aim the deadly flak guns, even in cloudy weather or at night. The radar-directed German defenses took a heavy toll of Allied bombers. To help protect the Allied bombers, British and American scientists developed electronic jamming to blind the German radars.
The aim of the jamming, basically any sort of countermeasure, is to stop the enemy having the full use of his radar. Now, if you can jam out part of the sky and route your attacking aircraft through that, then obviously that's a very useful thing to be doing. During World War II, the US Army Air Force used jamming on a very large scale to defeat the German fire control radars. They had this radar that gave them a very accurate range and enabled them to engage bombers with flak through cloud. If the bombers were flying above cloud, if you could jam out the flak control radar, then the bombers couldn't be engaged. So obviously that was a very useful technique there. As I said, basically it's to stop the enemy having the full use of his radar.
To jam the radars, the bombers' electronic systems emitted a strong counter beam, which interfered with the radar signal reflecting back to the German station. This is what the radar operator would have seen. The electronic jamming signal completely blinded the radar. Other anti-radar tactics were also used by the bombers. It was discovered that simple aluminum foil, cut in strips half the wavelength of German radar signals, would strongly reflect radar. Bombers could drop bundles of this material called chaff or winder. The chaff clouds would form an enormous blanket around the attack formation, so that German gunners did not know exactly where the real aircraft were located.
Here we have a unit of chaff that was dropped by the American B-17 and B-24 bombers over Germany in World War II. This is what's called a unit of chaff, and this packet contains enough strips to give a radar echo the size of a B-17 or a B-24 bomber. And after being released from the aircraft, the package opens up and all of these strips fall clear, and you end up with a cloud of them just fluttering through the sky, and that will appear on an enemy radar as a bomber, and hopefully the flak will engage these false echoes instead of the bombers.
The bomber crews worked out different tactics for using chaff, sometimes to blind the radars, and sometimes to deceive them.
If you try to imagine that everybody's image of a radar screen, which is a circular scope, green light, and a little blip comes up on it, and that is the target. If you have chaff there, suddenly the whole screen is covered in targets. In fact, to the point where it may be whited out almost. Masses and masses of little blips, one of which is the target, the rest are the chaff, reflecting the radar back on itself. So one aeroplane might be able to look like 5. Chaff can be used, another way of using it is what's called spoofing. When you spoof, you send out aircraft, maybe 5 aircraft, to generate the radar response of maybe 100. And it's a confusing tactic, more than anything else. It is designed to confuse the enemy, to break that engagement sequence, to confuse them as to where the attack force is coming from.
In naval warfare, radar could be used for more than air defense alone. New aircraft-mounted radars could help detect submarines on the surface, even if only their periscope was showing. This helped to turn the tide in the war against the German U-boats in the Battle of the Atlantic. German scientists responded by trying to develop coatings that would absorb rather than reflect radar beams. This was a precursor of modern stealth technology.
The Germans actually experimented with coating their submarine schnorkels and their periscopes with an anti-radar material in World War II. But there were problems with those early equipments. Specifically, it was very difficult to get it to stay on the submarine, because when the submarine submerged, all the stealth coating was washed away. Didn't really work for that reason.
In the years after World War II, radar continued to grow in importance. New radar technologies made chaff much less effective. As an alternative, the U.S. Air Force experimented with decoy missiles to confuse enemy radar. The tiny Quail missile contained radar beacons which exaggerated its radar reflection, making it appear as large as a bomber on enemy radar screens.
When you look at radar, there's always a question of how realistic whatever it is you're using to confuse the radar has to be. So you start with something simple like chaff, and the radar can see that it doesn't move as fast as you do. Eventually they disregard it. The next idea is maybe you can make something that really looks like an airplane. Now that would have certain advantages. If the deception's kept up long enough, not only will they not notice your airplane, but they may attack that thing. Since it's small, they may very well not hit it, so it may last quite a while.
Each B-52 strategic bomber could carry up to 4 Quails, besides its main payload. During an attack, a bomber formation could launch a swarm of Quail decoys on paths away from the actual direction of the mission. Enemy radar, the little Quail looked the same as a B-52 bomber. See on the radar screen here, it is impossible to distinguish the decoys from the real bombers. It was useful in protecting large bombers, but the Quail was too large to be practical for small aircraft such as fighters. Even as the countermeasures became more sophisticated, the radar threat also continued to grow. One of the most revolutionary advances was the combination of radar and missiles. Radar could be used not only to find the enemy aircraft, but also to guide missiles against them. The missile has a miniature antenna in the nose, which acts like a tiny radar receiver. When the radar guiding the missile emits its beam, the missile seeker senses the radar energy reflected from the target aircraft. The missile is launched. With its seeker locked onto the reflected signal, the missile homes in on the enemy aircraft. Radar-directed weapons first showed their power during the Vietnam War. U.S. attack aircraft operating against targets in North Vietnam were being shot down by radar-directed guided missiles, the notorious SAM-2 guideline. The Soviet-built SAM-2 also was used during the 1967 and 73 Mideast wars by the Arab forces, reinforced with deadly new radar-directed anti-aircraft guns. The use of radar missiles in the Vietnam War and the Mideast wars forced a rapid evolution in electronic warfare tactics.
Vietnam was the first time you saw missiles in great quantities. The missiles are all radar guided at that time, that's SAM-2. For the first time, if you're in an airplane, you need warning that not only that a radar is locked onto you, but that a missile is coming at you. You can get away from the missile. If you maneuver violently enough, you can avoid it. So you find tremendous interest first in picking up where the missile sites are, picking up their radars because that's a way of detecting them and mapping them, jamming those radars so the missiles can't be launched effectively. Once the missiles are launched, trying to jam the guidance system the missile uses so that, again, you don't get destroyed.
The deadly threats posed by radar-guided anti-aircraft missiles led to another round in the Wizard War. Quail decoys were too large for strike aircraft of the 1970s, but pulse radar images could now be created electronically by a new technique called deception jamming. Advances in microelectronics allowed sophisticated jamming equipment to be crammed into a small pod that could be carried by every aircraft.
For a deception jammer to work, what it is trying to do is it receives the signal coming from the radar, it mimics it and retransmits it in such a way as it deceives the radar to the point where it thinks that the target is somewhere else than where it is. Deception jamming is very complicated, very classified, very secret in many respects. Deception jamming is subtle. It takes a good operator and it takes very sophisticated circuitry inside the system to tell that it's been jammed.
The growing sophistication of anti-radar tactics have created their own special problems. The electronic pods, chaff, and sensors take space away from bombs and other payload on the strike aircraft. Also, the growing sophistication of radar countermeasures required larger and larger jammers and dedicated human operators. Air forces were forced to develop specialized radar jamming aircraft, such as the EF-111 Raven and the Navy's EA-6B Prowler.
Well, the reason why you need to have a dedicated aircraft is that if you want to carry a really powerful battery of jammers, and also you want to have the power, that is, you're going to produce enough power within the aircraft to run these jammers, you've just got no room for any bombs or anything. So that is the whole rationale behind the dedicated jamming aircraft. You've made the example of the EF-111, and of course there's the EA-6B. And these aircraft act as a sort of a jamming escort to jam the radars in the target area while the striking force goes in to attack the target.
Dedicated jamming aircraft, such as the EA-6B Prowler, do not usually carry conventional weapons. Their defenses are primarily electronic. Their jamming systems are dozens of times more powerful than the simple jammer pods carried on strike aircraft.
Electronic warfare can be divided roughly into self-defense measures, which are carried by the individual aeroplane to protect it from the enemy. Something like the F-111A Raven, which is one of the most powerful jamming aeroplanes in the world, is designed to provide support. It's called a support jammer or a standoff jammer. The idea is that it has an enormously powerful radar jamming system on board, and we are talking powerful here. Whether this is an apocryphal story, but it's certainly been stated that in the early test stages of the EF-111, an aeroplane took off from Vandenberg Air Base and took out all the ATC radars to Seattle, and that is a powerful system. In fact, those aeroplanes in Europe that were stationed here had very strong restrictions on their transmission. So they can generate a wall of jamming, one of their roles. Grumman, when they launched the aeroplane, maintained that 5 aircraft of the Raven type flying in racetrack patterns could take out every Soviet air defense radar from the Black Sea to the Baltic.
Another method to silence radars was to use the enemy radar signals to betray their own location. By putting a special radar homing head in a missile, it could home in on the radar and destroy it. This type of missile is called an ARM, or anti-radiation missile.
Well, the argument for the anti-radiation missile is that it's much better to knock out the radar permanently than try and jam it temporarily. And the successor to the Shrike and the Standard Arm is, of course, the high-speed anti-radiation missile, the HARM. Large numbers of these were used during the Gulf War, and this weapon, for the first time, I think, it was much more effective. For the first time, it was really effective.
To use these anti-radar missiles to best effect, dedicated anti-radar aircraft are often used. In the U.S. Air Force, these are called wild weasels. They carry special sensors to locate enemy radars, as well as anti-radiation missiles to attack and destroy them.
Well, the Wild Weasel is a US Air Force program, and these are the aircraft that are fitted with the anti-radiation missiles, and their job is defense suppression. In other words, they are there to keep the enemy's heads down, to stop them using their missile systems while the attack force is in the area. So if we take a modern attack package, you will have the EF-111s, you will have the Wild Weasel aircraft protecting, they'll have their fighter escorts, and you have the striking force. These all arrive in the target area at the same time, and the idea is to prevent the enemy from having the full use of his radar and his defensive systems while his strike force goes in to do its attack.
Anti-radar countermeasures have proven enormously successful. By the end of the Vietnam War, fewer than 1 out of every 50 anti-aircraft missiles hit their target. But radar was not the only means to guide a missile. Infrared heat-seeking guidance was introduced on anti-aircraft missiles, so countermeasures were needed for this new threat.
Well, against the infrared guided missile, it is looking for a powerful source of infrared energy, and so, of course, a small decoy flare makes a very attractive target to it, and everybody has seen those transport aircraft going into Sarajevo, firing out the infrared decoys as they come in. There is another technique to defeat the infrared missile, and that is a modulated source. If you like, it's an infrared source that is blinked on and off at a very carefully set rate. And what this does, it gets inside the logic of the infrared homing missile, and it gives it the electronic warfare equivalent of schizophrenia. The missile just loses all further interest in the target, and it just peels away, and that's the last you ever see of it. So those are the two basic ways of dealing with the infrared missile.
These many types of electronic countermeasures are effective, but are also costly and cumbersome to use. In the 1970s, the U.S. Air Force began to wonder if some passive form of countermeasure could be developed to hide from radar. This low observability is popularly called stealth.
Stealth is a significant development. It's true, the true description of it is low observability. In the radar world, all aeroplanes have what is known as a radar cross-section. That is the response that they will give. A B-52 bomber will give a massive response to a radar. Stealth attempts by two methods, shaping and radar absorbent material, to reduce that to the point where the radar has great difficulty tracking it. Now, one of the great myths about stealth is the invisible aircraft. No aeroplane, not the F-117, not the B-2, are invisible. What they do, going back to that point we made right at the beginning, they make the engagement sequence impossible. Now, we've talked about two methods of doing it. One, shaping. If you look at the F-117, you see that this aeroplane is made up of flat plates all around it. What it does, the radar signal comes up to it and is reflected away from it in any direction than back to the original radar. So therefore, it can't be seen by the radar. It can be seen by radars behind it, to the side of it, but it can't be seen by the one from the missile system that's trying to shoot it down.
Stealth technology continues to improve, but for every innovation in countermeasures, a new innovation is likely to emerge in radar detection. The wizard war is a relentless struggle, measure against countermeasure. Success in the wizard war means the difference between survivability and destruction on the modern battlefield.
Firepower, the world's largest and most complete video cassette series on contemporary military technology. There are many more titles in this series which you can order now. If you want the latest in today's advanced weapons systems in the air, on land, and at sea, look no further. For program titles and information on how to order, call us at 1-800-377-7773 and get Firepower.